So, how's this going to look formally? So, how do we think about models? Well, we think about models a little bit the same way that we think about modeling speech, the way of modeling your voice. Right? When we're modeling speech, what we do is we calculate the LPC coefficients of your voice. So that's a little subspace model. And then we exercise that model with Gaussian noise. So that's how all sort of speech synthesis works. And we're sort of doing the same thing here. So we're exercising a subspace. And phi here is our measurement matrix. And we have this subspace. And we're trying to tell different subspaces apart at the output of this measurement process. So that's so this is technically what our problem looks like. And we get to design this phi to optimize detection. We estimate the subspace. We're interested in the average probability of error. We want that to be small. Here's the theorem. So from an information theoretic point of view, we're going to let everything go to infinity proportionally. We have L things that we're trying to tell apart. And this theorem looks a little bit like Zheng and Say. Actually, we were sort of disappointed that we couldn't just appeal to Zheng and Say. It's a slightly different problem. We had to work, maybe if we were smarter, we would have had to work less hard, but we had to work surprisingly hard. But it says that if you look at L, the number of things we're trying to tell apart, take the logarithm of that, that's what it looks like. And this actually, if you're familiar with Zheng and Say, this is consistent with the Zheng and Say result. So here, the sigma squared is our in a sense our mismatch, and that looks like noise in the Zheng and Say result. Now, I want to tease you with the idea that essentially looks a lot like the Shannon relationship, because if you think about subspaces, you think about a k-dimensional space. In an n-dimensional space, then it's got n minus k degrees of freedom. So if you're thinking in terms of Nyquist, n minus k over 2, that's like w. So this is really very much akin to that formula. And when you're thinking about ensembles that you can tell apart, you know, there's an upper bound here and a lower bound here, and provided k is bigger than m over k is bigger than m over 2, these things match. So the upper bound comes from Fano, the lower bound comes from constructing a random ensemble which you can tell apart. So that's so here, duality with communications, we have a code book, we send something, we receive something with errors, we look at the closest thing, and that's very simple. Now here we have faces. We receive something that's just a feature. We try and figure out which one. And what does capacity mean? Well, when we fail, there isn't enough mutual information between what we receive and our subspace and mean. There isn't enough mutual information to be able to decide. There's not enough mutual information no matter how hard we try to design phi. So if there isn't enough mutual information, we fail. And capacity is when we stop failing. So that's the inf. So that's how that works there. So this is the remark about the bandwidth of subspaces. And so now we've learned something about the shape of that boundary. So how many things we can distinguish as a function of number of measurements. And how to say that? So this is what I hope is that this is an indication that information theorists actually have something to say about machine learning. Because in statistics and machine learning, subspace models have a long and honorable history. And information theory can say something about how effective these models are.
What is K over here?
What's that?
What is K over here?
K is the dimension of your subspace. So when we were looking at faces, M is like 21, and K is 9. So
what is N then? So there's also N.
Yeah. So you have your N is the dimension of the ambient space, and your model is an M-dimensional, but everything lives inside of that in M dimensions, and your actual convex body is K dimensional. So that's how those things work. Okay. So that's that. What about real world data? So we did this little experiment where on the Yale B face database, where we looked at taking increasing numbers of measurements and how many things we could tell apart. So here, I don't know that I want to say too many things about the experiment. So what I want to say about the experiment is that theory predicts a phase transition. We get a phase transition too. Now, phase transitions are, this is not like Emre's phase transition yesterday. It's considerably sloppier. And perhaps it's sloppier because our model was kind of sloppy. We expected that theory would predict that this phase transition would happen over 1 or 2 things, and it happens over maybe 5 to 10. But still, there is a phase transition. So we were happy to observe this. So if you're curious about learning more about this, there's a paper it's on arXiv. It's about to appear in the information theory transactions, and it has the background, and it has the proof of the theorems and now let's go back to let's go back here. And let's think about designing this measurement matrix. So let's go forward again. So let's take a database. This is the MNIST database of handwritten digits. curated by Jan LeCun and Corina Cortez. And it's a standard data set in machine learning. And the question that I would now want to ask is, if I could make a, so I'm going to now make linear measurements, and I'm going to want to tell different digits apart. What's the best I can do? How do I design measurements? How do I design this matrix phi? And this is a paper that's that I think is in either NIPS or ICML from 2012. So I want to give you a way of thinking about the SVD. So I'm going to design my measurement matrix phi, which is an m by n matrix, and I'm going to want to think about what is the role of the unitary matrices U and V on the left and the right-hand side, and what is the role of this diagonal matrix delta in the middle. So I want to give you a way of thinking about that. So here's what we're doing. We're doing this measurement, y equals phi x plus n. And so we have a model for x, and we're trying to figure out what is the best phi. How do we do that? Well, think about x. We have a model for x. So we have a covariance matrix for x. That's that sigma x there. We also have a covariance matrix for the noise. And then we have these diagonal things on the diagonal of phi. So let me see what the next slide says. No, it doesn't do that. All right. So I'm going to. So what is the function? So here I'm claiming that and here I've got a Gaussian source. So I'm claiming that when I think about designing this measurement matrix phi, the right matrix, the right eigenvectors, those should coincide with the left eigenvectors of the covariance matrix of x. Now, why is that? What is the function of those right eigenvectors? The function of the right eigenvectors is to collect as much energy as possible. And the best choice for collecting energy is for the right eigenvectors of phi to coincide with the eigenvectors of the source matrix. What's the function of the left eigenvectors of phi? Well, you see, you collect all this energy, and you collect it into these little modes, one-dimensional modes. And some of these modes have a lot of energy, and some of them have less energy. So now you've got these modes, and you get to distribute the noise. And you get to distribute the noise to maximize the mutual information. So if you have high energy, you want to be with low noise. So what we're going to do is we're going to organize the eigenvectors of x from lowest to highest. So it's going to be the lowest eigenvalue of x, that's lambda 1, and the next one is the next highest. So they're going to be going up. For the noise, they're going to be going, oh, I did this wrong. No, I didn't. I'm sorry. I always get this wrong. Sorry. The x eigenvectors, they're going down. The noise eigenvectors are going up. We're interested in the ratio of one to the other. So we are interested in the ratio of the noise to the signal, and we do water film. So we this is the standard water filling thing. We have a power constraint. The power constraint tells us how much water we're going to pour into this arrangement. The height of the water above the base tells us how much energy we're going to invest in that channel. So channel 1 here, the ratio of noise to signal is lowest. That means it's got the highest ratio of signal to noise. So we want to be investing a lot of power into that channel. So the moral of this story is that, the story that I just described here is very much an information theory story. So it's, and actually I have to say that it's rather an embarrassing story, because there's this beautiful paper from 2004, Guo, Shamai, Verdu, which relates the gradient of mutual information to the minimum mean squared error matrix. And what I just described to you here was a special case of that. What's embarrassing about this is that when I was at Princeton, I actually never talked to Sergio about this. And since I moved to Duke, I've used it quite a few times. And so it's really a wasted opportunity. Now, what I explained to you here was a Gaussian source. Sergio's first paper was Gaussian scalars, second paper was Gaussian vectors, and third paper was non-Gaussians. And so in non-Gaussians, so his source X is not a Gaussian, and he has this beautiful paper with Tolino on mercury water filling, where this picture here is modified. So you could think of the black regions here as non-mercury. And what Sergio does is he pours mercury on top of each of these. And the mercury represents the difference between the Gaussian distribution and his distribution. And then he pours water on top of the mercury. And of course, because mercury doesn't float, everything works out. So that's how you make measurements. When you don't have Gaussian measurements, things get a little bit more sophisticated. Your ordering of the noise eigenvalues is perhaps a little bit different, but it's essentially the same principle. And so, if you're an information theorist, and you in a sense, you want to get into machine learning, then you in a sense have all of the tools. Because if you want to design measurement matrices, either for a single measurement or for a batch of measurements, you actually have all of the tools. And you can do gradient descent on the MMSE matrix just as well as those guys from machine learning. So that's the moral of this book. So information theory, if you're just interested in the question of what measurement should you take, that question is really information theoretic. Now, the last part is about subspace classification. No, not subspace. So we've done that. All right. Now we're going to do training. And we're going to try and make a connection to rate distortion theory. And this is the newest part of the talk, and it's, in a sense, the least well developed. But I think that there's something interesting there. So first of all, I have to remind you what rate distortion theory is. So in rate distortion theory here we're talking about Hamming distortion. I have random bits. I might have 12 random bits. But I'm going to represent them just using 6 bits because I had 12 bits to begin with and I have 6 bits in my representation. When I reconstruct, I'm going to have to accept some distortion. And rate distortion theory tells us exactly in some cases how much distortion we incur when we compress a source. So for example, an easy calculation is that if you have a rate 1/2 two-state convolutional code, it's an easy analysis to show that on average you flip 1/6 of a bit. So here you take a random infinite string, you represent it by a code word. The code word is rate 1/2, the random string is rate 1. You would flip 1/6 of the bits. So that's rate distortion theory. So you should have that idea just in the back of your mind. Because, and so for Hamming distortion, we know completely the answer. We can, there's things that we can't do that are infeasible, and things that are feasible, and that's the boundary of the region. Okay, so we're going to think about training, and the question when you do training is that you have these training samples and you train on them and you develop a model, and then you're given data samples and you want to know how well you can do. And you would actually like to be able to extrapolate your performance on the training to the actual data. So we want to try and say something about how that works. Or we want to try and represent it in terms of information theory. So how much do we need? Now, what we're going to do here is do something in not quite the way that machine learners do it. So in machine learning, people study classifiers, right? They have classifiers like hyperplanes, for instance. And so if you're in machine learning, you say, I have this classifier family. It's hyperplanes. And then I'm interested in using these hyperplanes to separate different classes. And what happens in machine learning is you start with a classifier family, and then you imagine the most perverse distribution you could possibly imagine to break your classifier. And you develop bounds that are a function of that worst case. So in classical machine learning, you start with a classifier family, and you make the most pessimistic assumptions you possibly can about the distribution you're looking at. Now, what we want to do, and of course you get upper bounds. We're actually interested in lower bounds. So what we want to do is we want to start with the distribution. We want to start with a parameterized distribution that in a sense gives us a sufficient statistic. And then we're going to use rate distortion theory to see if we can get lower bounds. That's so. This is classical machine learning. So here we've just used lines in the plane. This is an example of hyperplanes. And this picture just shows that if you have 3 points in the plane, you can divide them in all possible ways using lines. And the example that's not on this slide is 4 points, which you can't divide if you can divide your 4 points into 2 pairs and they have an overlapping convex hull, then you're in trouble. So, classical machine learning, start with the classifier, make a pessimistic assumption about your distribution, and Vapnik with Chervonenkis defined this notion of dimension, which has to do with imagining that worst possible distribution. And in the machine learning community, the left-hand side is the error that you make on your data. The error with the bar on top of it, that's the error you made on your training set. And you want to understand the error that you incur on data in terms of the error on your training sample. And there's this expression here. And you see H is this. Now, machine learning people know that this bound is usually loose, and they do all sorts of things to get around that. We want to go in the opposite way. So we're interested in we have we're looking at these signals X, L are the classes, and what we want is for the distribution to be parameterized by some alpha. Now the samples will be distributed according to some parametric model that we don't know. But what we want is that the distribution be parameterized by some alpha. So you can think of alpha as like a sufficient statistic. So if we were thinking about these numbers again, you could think of representing a number just by a little patch of pixels, which would be black or white. So you could think of there being a Bernoulli model for blackness versus whiteness. And that would parameterize whatever you saw. Now your numbers are some kind of distribution on top of that, which you don't know. but what we want is there to be some underlying parameter that's d-dimensional. We want to come up with bounds that are a function of that. So that's the. So here, simple example: Gaussian centered at alpha minus alpha. We don't know who's choosing these things. So the true best classifier is this black line, the black dotted line here, but we see these samples, we learn the brown line. Now, what we want to do is we want to think of the map classifier, that's the black line. That's like a distribution. So we want to think of that distribution being described by a certain number of bits. And every time we see a training sample, we get to learn something about the map distribution. So we want to try and use results from universal learning to learn classifiers. If we don't have enough bits to learn a classifier, then we're going to be trying to compress a source, and we're going to have to incur some distortion. So that's our philosophy. So what we do is we look at these training samples and we make a classifier. That's Q. The map classifier is W. We're thinking both of them as sort of distributions, and we're thinking about then there's results from machine learning which represent the error in classification, using your classifier rather than the optimal classifier in terms of the total variation between those two distributions. So we're using total variation as a surrogate for that error on the test data, and so we have this little theorem here. So here, again, you see we're assuming that alpha is a sufficient statistic for our world, and so here we're balancing three quantities: the entropy of the map, how many bits are needed to describe the optimal classifier, how many bits the training set provides, and the difference between the two. And under some mild conditions, we obtain the same coarse scaling as the VC bounds, but these are lower bounds rather than upper bounds. So let me. So this is the. So we've learned something about the shape of that region, where D is the dimension of this parameterizing set. Here's a so you really need simple examples to be able to calculate things. So here we just follow through on this very simple example where you have binary Gaussians centered on alpha and minus alpha, where we can calculate everything. This total variation between the two things is given very simply. This W0 is something called the Lambert W function. So you just think of that as a constant. And these are the results. So you can see vanishing up there at the top are these things that are called PAC. So these correspond to the VC bounds. And you can see that they're actually not very useful. And of course with our, we have a very simple model, and of course we chose it to be parameterized. So in a way it's not so surprising that the fit between our bound and the empirical truth is pretty good. And if the noise is a little worse, then we do a little worse. It's still pretty good. So we've got, so so those are 3 stories, where the first was about classification, and that in a sense is the most well-developed of the stories, and that's a paper that either has appeared in IT or is just about to appear in IT. There's a middle piece, which is not on the slide, which is about, if you only have a certain number of measurements, how should you make them? And that connects to the work of Ledoux and Guo and Shumai. And that's in a series of NIPS and ICML papers. And then the last is this connection to rate distortion theory, which I have to say we're still working on. But what I hope I've shown you is that that in a way the message is that because you know information theory, you actually know a whole lot of other things. And actually, because you know wireless communication, in a sense, all of this is just, perhaps not the last bit, but the first 2 bits, they're all wireless communication. That middle bit, if you think about it, is, the difference between what I described in the middle there and what Danny Palomar does when he designs pre-coding matrices is very, very small. So the message is that if you know about wireless communication, you really know about machine learning. And so these Anson spectrum, they're really an opportunity rather than a non-opportunity. Okay, thank you.
Thank you, Professor Calderbank. Any questions for the speaker?
Mm-hmm. So, how do you see information theorists contributing to implementable machine learning algorithms? For instance, evaluating the MMSC for an interdimensional vector is going to be of exponential complexity in terms of computations. So, how do you see that?
Well, so here, we were looking at a different question, right? So we were interested in fundamental limits, and we were interested in showing that there were fundamental limits. And in a way, that's a subject that's actually of interest in machine learning too, because oftentimes when you produce these deep convolutional networks that do amazing things, if you change your images a little bit, then they fall apart. And so the notion of mismatch between what you see and what you have is I think, interesting. Now, question of how you build things, that's, we don't, I'm not sure that we've completely solved that in information theory either, right? So, but that means that we have room to work in each area. All what I wanted to suggest was that there are things that we know that relate to problems that they care about.
Because you made a passing mention of applying gradient descent on MMSC,
Yeah.
So, but that's going to be, as well as implementation is concerned, that's going to be possible.
It's not easy. I mean, we did it on this little database, and it worked better. So I mean, we did better than the previous state of the art. And I mean, and it wasn't computational heroism, but it was, in a sense, it's relatively manageable. But I agree, but you know, that's a whole interesting area. I mean, gradient descent, the stuff that Ben Recht has done. I mean that it's an interesting area for us. It's an interesting area for them too.
Any other questions?
For the analysis of bug, we have to know the true model for the true model, right?
Well, so I'm not quite sure what's your question.
For the analysis, we have to know the true model. So, what is the true model for?
Philosophical question. What's the true model? I don't know. If true models exist, I don't. So I don't know. But there's. So I don't know. So I don't know what truth is. But I do know that there's always going to be a gap between what I think it is and what it might be.
But for the analysis, we have to pick some true models to analyze the bug.
Yeah. Well, I mean, I suppose what I'm saying is that there are models in machine learning and statistics. Many of them based on subspaces. Actually, I mean, if you do manifolds, I mean, in a sense, manifolds are trees of subspaces. Right? So, in the end, subspaces are pretty fundamental. So there's this community that reasons about subspaces. We actually are also a community that reasons about subspaces, because we do wireless stuff. That's how we communicate over wireless channels. So it's worth looking at what they do to see whether there are things that we know how to do that they haven't learned yet. That's really the meta point from the talk. So it's to try and create a bridge between the two.
We do have a little bit of time before lunch. I mean, we don't have to continue, but just I just want to give enough time for the audience to sometimes people will be any.
In machine learning, in many cases, we can just give we focus on the numerical results, and we can't give the theoretical results. So many researchers may doubt about machine learning. For example, like deep network, we don't know how it works. It's just a black box. So, what's your opinion of this phenomenon?
So I mean, I think that there's a let's say a difference of opinion between, let's say, Yann LeCun and Stéphane Malin, right? So Stéphane Malin. So Yann LeCun, I mean, likes deep convolutional nets with lots of levels. Now, actually, to be honest, if you work for Facebook or Google, you might learn a deep convolutional net with 9, 10, 11 more levels. When you implement it, you actually shrink those levels. So when you actually operationalize something, you operationalize it with fewer levels. So so there's two questions. One is, how many levels do you really need? And do you have to learn more levels in order to get to the thing with the smaller number of levels that you might implement? I mean, those are questions. I think that I think that there are things that we can say about the structures of the graphs that they build. So, for example, there's a recent paper by Guillermo Sapiro and why have I forgotten his name? He's a student of Mickey Elad on showing that certain deep convolutional structures define contractions. So I mean, that's something mathematical, right? We can analyze contractions. So I think that there's going to be more results, there are more results out there like that. You know, there's results by right about two-stage networks that perform relatively well. I think that that's also really interesting to understand that. But I mean, I think that this is I mean, just because they don't typically do theory doesn't mean to say that they wouldn't appreciate it if someone else could do it. One of our strengths is we're able to do theory. Now the thing about machine learning is that if you want to publish a paper in NIPS or ICML, which are their most competitive conferences, then it's a little bit like SIGCOMM. So to get a paper into SIGCOMM, you need a really cute idea, and you need some kind of analysis. That's a little bit discretionary, but you for sure need some kind of implementation that convinces, right? So you need something, you need a cute idea, and you need some kind of implementation. And if you have those two ingredients, then you're not golden, but you won't get triaged out. It's actually not a bad thing for us as a community to think about numerical stuff. Actually, I mean, in some sense, we have gotten all excited about finite block length information theory. But you know, if you think about it, was there ever a wireless standard that didn't think about finite block length? I mean, they might not have had theory for it, but they for sure thought about it, right? I mean, we have a habit as a community, and it's not a good habit, of discovering that things are theoretically interesting late. An example of that is hybrid ARQ. Right? I mean, for the longest time, we've had protocols that do hybrid ARQ. But it was only in the 1990s, 2000s, that we in the information theory community decided that that was a legitimate thing to think about. And then we discovered, you know, all sorts of interesting theory about it. You know, the same thing's true of finite block length, right? If you're a communication engineer, you've always cared about what happens at finite block length, right? And now we as a community care about it too, so that's progress, but we are still catching up a little bit. Sorry, that was intentional.
It's leading very naturally to the afternoon session where much more philosophizing and holding positive opinions will hopefully happen. I'm really looking forward to that. Well, let's say we can stop now. There'll be lunch. You'll have an opportunity to interact with Rob, joining us for lunch, and other speakers. In the afternoon, there'll be you will be providing part of the infotainment. Right, as I requested, as I kept threatening emotional blackmail, I tried all the tricks in my bag to get something out of you guys. And there's a few videos, and there'll be hopefully one or two performances. So we'll see what happens in the afternoon, and then finally we'll end with the panel discussion with people talking about their experiences in the information. All right, so let's thank Professor Calderbank again.
Thank you so much.
I keep messing up the Chinese traditions of writing things to
Thank you. Yes. Demonstrate that you've done this.
So immediately start writing. Would you mind if it's like anyway, maybe rock
I'm sorry, where was that? He's going back, yeah, but I'm...
But yes, I can drop you at the lunch break and then continue.
Okay, cool, that's a good idea.
And if you want to carry that, fine, you can also store it here.
I'd be happy to store it.
Yeah, she's,
Yeah, so